So different kinds of logic we're going to play around with. We've got some set theories. I'm just going to do a quick outline of the week. Some set theory. Along with that comes Venn diagrams. What's called Boolean logic. Logical statements. A little bit of work with a spreadsheet. And then logical truth tables, right? And logical fallacies. So mostly in that order, we're going to play around with these topics in logic. The homework in the logic is a little easier than the problem solving stuff. We kind of start off with the hardest chapter there, I think. But this stuff is different because a lot of math classes don't usually cover logic. So some of this you may have seen before and some of it you may not have. So let's first take a look at Boolean logic. Named after a guy from a while ago called George Boole. And so something that's Boolean has only two possibilities. Okay, so those two possibilities are usually true or false. Sometimes they can go by other names. Like in a computer, a true is usually a value of 1 and a false is a value of 0 on a computer. Could be a yes or a no. And the yes or no could be different. The yes could be true, but the yes could be false in a different situation. Okay, but true and false are the basic things about Boolean logic. And so we'll play with different ideas and the true and false. So those are the Boolean possibilities. And then we have what are called Boolean operators. And those are things that can only handle two things at a time. And most of the things we do with math, we can handle only two things at a time. In logic, our main Boolean operators are and. When we put two things together with the word and. Other common one is using or. Oops, not on. Strange. But outside of logic, other kinds of Boolean operators are like, think about addition. When you add, don't you add just two things at a time? I mean, even if I write down something like 3 plus 5 plus 10, you usually do the first two once you get an answer, then you add the third one. People don't add three numbers simultaneously in their heads at once, right? It's a two at a time thing. So most operations we do are Boolean in math. The main ones we'll focus on here are and or. There's other operators aren't really Boolean, but they do change things. So other operators. And in math, an operator is something that changes the way things were. Addition changes what you started with. Multiplication changes what you started with. If we had donuts and we had French fries and we put them together, now we have a whole lot of carbohydrates, right? So that's an operation. It changes things. We put things together, we get a new thing. Other operation is a negation. That will do. Sometimes we just say it's a not. And that's not really an operator. Like to do and, I need a thing before the and, I need a thing after the and, right? But with a not, I can do anything. Like I could have something that is not T, and I'm only operating on the T, right? What's not T? Well, everything else in the world is not T. So we have to deal with that idea when we're playing around with different statements. Next, let's see. So we'll start applying those. Let's do a little bit of set theory, and we can apply the Boolean stuff. So set theory applies a lot to logic. We can use it to analyze it. For example, let's do some math. You guys have heard of a group of numbers called the even numbers. Is 3 an even number? No, is 2 an even number? Yeah, so you can tell me whether something is even or not. So in logic and inside of math, we need things to be well defined. So it's quite clear what's in the set and what's not in the set. So you could all start listing even numbers for me, right? What's the first even number? Almost, that's the second one. 0 is actually even, yeah. So we often count 0 to be the even numbers. Usually we're thinking about the counting numbers, and the counting numbers start with 1, so we tend to ignore 0, but it's technically even. Okay, I'll explain that later. Then we have 4 and 6 and 8, and that list of numbers goes on forever. It doesn't end. So one way to describe a set is to just list the set out. In math, when we're talking about sets, we usually surround the set with curly brackets, kind of common notation. So there's one description of the even numbers. Another description, you have a more complicated set notation where they'll do something like this, curly bracket, and then they'll put a variable down like x, and then you'll see a straight bar after that, and then they'll do things like x, that is basically is a counting number. Oops. Let's make that a little neater. Comma and any other condition. So if I wanted x to be one of these even numbers, I would also say that it's divisible by 2. And so that's another way to talk about this set. So counting numbers, so that implies everybody knows what the counting numbers are. Well, we count with 1, then 2, then 3. Then what does it mean to be divisible by 2?
Even number.
Okay, so but you can divide it by 2, that it's an even number. Any other ways you can tell if something's even? What does it mean to divide by 2? Like I could take 12 and divide it by 2. 2 goes into 12 6 times. I could take 11, I could divide that by 2. Also, 2 goes into 11, what, 5 times? Oops. With a remainder of 1. So I was able to divide 11 by 2. Why isn't it even?
Oh, in integer.
You can't have a remainder is the key, yeah. So when we say something is divisible, that means there's no remainder. I could have written with the 6, the remainder is 0. I chose not to write it. Right? I kind of skipped that step. So divisible means there's no remainder. Is the technical definition there. But these are 2 different ways to say the same thing, the even numbers. Okay? But some way, whether we're talking about sets or logic, we have to be clear what every statement or every word means. If we're not, we can't analyze it properly. So with set theory, sets need to be well defined. Sets must be well defined. Meaning, we know what things are in the set and what things are not. Okay, so that's well defined. You know what's in the set, you know what's not in the set. All right, how about prime numbers? Oops, missed a letter. Prime numbers. Let's see, what's the first prime number? Usually when we're talking about negative prime numbers, we want them to be counting numbers. Yeah, but negative numbers can be even, like -2, -4, -6. They're even also. Yeah, so 1 is not prime. It's special. I'll get to why in a minute. 3 is prime. What else? 7, 5. How about 2? It's prime. Yeah, so prime numbers, I believe, start with 2, and then 3, and then 5, and then 7. And they go on with a pattern that's not as predictable as 2, 4, 6, 8, 10, but there is a pattern. So then what does it mean to be prime? So we need a definition. Yeah, so if I use that fancy notation where I said prime numbers are the set of all x values, that bar, by the way, means such that. So x values such that, what can I say about x so somebody else would be able to figure out if it's prime or not? How do we make this set well defined by describing it? You can say something, Ian? No? X has exactly 2 distinct factors. That's one way to describe a number that's prime. So let's just play around with a couple of numbers and decide whether they are prime or not prime. So I believe a number is prime if it has exactly 2 distinct factors. So if I picked a number like 4, well, 4 could be factored as 1 times 4 or as 2 times 2. So here I have 1, 2, 3 different factors. Okay, so that means this sucker here is not prime. On the other hand, if we pick on 3, how can you factor 3? Well, 1 times 3, that's the only choice, right? So there's my 2 distinct factors, which means, yeah, this thing is prime. Yeah, they could, well, and itself. Yeah, so yeah, it's another way to say it. The factors are 1 in itself. Here's the catch, though. This works for 2 because 2 could be factored as 1 times 2, and that's the only way. But how do you factor 1? Well, I guess you could say it's 1 times 1, but it's the same number. It's not 2 distinct factors, so that's why we say this is not prime. Okay, so that's another question. So what do I call numbers that aren't prime? Well, sometimes we use the word composite, and composite generally means more than 2 factors. So 4 would be composite, right? 6 would be composite. 10 would be composite. But 1, it's not prime. It also isn't composite. It's just 1. It's its own category of number. Yeah. So one way to break the counting numbers into different groups would be to say, well, you got 1, you got prime numbers, and you have composite numbers. So we can use the idea of prime. That breaks the counting numbers into 3 different groups. So just draw a picture of that. So counting, ooh, hit a crazy button on my pen. Counting. So I'm going to draw what's called a Venn diagram. Hopefully you've seen these before. If not, they can be very handy in analyzing problems. Can a number be both prime and composite? No, right? Because you can have two factors or you can have more than two factors, but you can't have two factors and more than two factors at the same time. Just doesn't work, right? So I could say there's a group of numbers inside the counting numbers. They're called the primes. And there's another group of numbers inside the counting numbers. They're called the composites. And then if I start taking counting numbers and throwing them in here, well, 2 would be in this group, right? What else would be in this group? 3 would be in here, and 5. 4 would be over here. 6 would be over here. 7 would be over here. That's not a very good 7. It's better. Let's see, 8 would be over here, 9 would be over here, 10 would be over here, 11 would be here, 12 would be here. Now we could spend all day doing this, but we get the point, right? There's a way to find prime numbers. Check to see if they have divisors. If it's not prime, then it's going to be in the composite list, except for one number that's neither prime nor composite. What's that one? Yeah, 1, so 1 lives outside here somewhere. Yeah, all by itself in that area. And when you take groups or sets and you put them in a picture like this picture is called a Venn diagram. So in logic, we have the logical operator called AND, right? And we just thought about, can you have a number that is prime and composite? So where do the prime numbers and the composites overlap? They don't overlap. Can you have a number that is not prime and not composite?
Yes.
1. Yeah, that one works. Yeah. So what we're going to do is we're going to be analyzing statements, and those statements will involve and, they'll involve or, they'll involve not. And Venn diagrams can help us kind of sort out what goes where in a situation like that. And they may be numbers, but it could be other things. It could be people that go in these sets. It could be ideas that go in these sets that aren't numbers. Right? But a Venn diagram can be powerful. Another version of that Venn diagram, usually a Venn diagram starts with some kind of rectangle, and then it has one or more circles. Usually the circles are made to overlap like that. And so let's just analyze this for a moment. So let's suppose, again, we're playing with the counting numbers. Whatever thing represents the rectangle, that's called your universe. So that's my universe here. Sometimes you'll just see the letter U for universe. And then this set over here, like before, let's let the one on the left be the primes. And then set on the right be the composites. And then some other things to consider. I could be looking for numbers that are prime or composite. Okay. When we use or in math, that means to meet the or condition, things have to meet the first condition, the second condition, or both. So it's different than when like I use or in common language. Like if I go home after school, I made a cake, and my kids are going to say, hey, can I have some cake? I'm going to say, sure. But they might say, can I have some cake and ice cream? And then I might reply, well, you can have cake or you can have ice cream, right? So one of them says, okay, I'm having ice cream. Later she says, I want cake now. What should I say? Sorry, right? I said, you could have one or the other. So when we use or in regular language, it's called an exclusive or. It means you can have one, you can have the other, but you cannot have both. In math, or is inclusive. It could be one, the other, or both. Okay. So we'll explore that idea with this example and a couple of others. Oh, my pen's disappeared. Let's see, what was the trick the other day? Control T should bring them back. There they are. Okay, so I need a new color. So just a reminder, or in math means meet one condition or both. So I could meet the first condition, I'm in the or set. I could meet the second condition, I'm in the or set. I could meet both conditions. So sometimes in logic, when I'm trying to get everyone used to the idea of the inclusive or, a capital or in logic in regular language would be if I put the and or in there. So if I said to my kids, you can have ice cream and or cake. Right? Most of them would say, good, I'm having both. So in logic, when we use the word or, we could replace it with the phrase and or. And so that takes a little getting used to. That's called an inclusive or. So let's see. We know the number 2 is prime. We know the number 4 is composite, right?
Mm-hmm.
So if I'm trying to find out what numbers fit that description, prime or composite, is 2 prime or composite? The answer is yes, because it meets the prime condition. Is 4 prime or composite? Yes, because it meets the composite condition. Right? Mm-hmm. So picture-wise, if I wanted to show somebody in the Venn diagram, what part of my diagram is this whole collection of things? Well, that would be this figure 8 right here. This figure 8 are the things that are prime or composite. So let's see, is 3 in the set prime or composite? Yeah. How about 17? How about 1,125,632? Yeah. How about 1? Nah, 1 lives outside, right? So 1's not in there. So 1 lives out here. Oops, I meant the pen. 1 lives out here, so it's neither prime nor composite. All right, let's try with a slightly different group of numbers. Let's try Venn diagram. Counting numbers again. And we'll stick with the prime set again. This time, instead of composite, let's do the even numbers. And let's see, before I do the or, I'm going to do, can I have a number that is prime and even? Give me an example. 2. 2 is prime and it's even. Okay, so that means 2 would have to live right there because it's in the even set and it happens to be in the prime set. What's that? Yeah, 2's the only one because otherwise, once we get to the net, what's the next even number? 4. 2 to be even means 2 goes into it, so every other even number cannot be prime because of the 2 definitions. Yeah. So otherwise, when we start listing numbers, let's see, we'll have 4 over here, we'll have 3 over here, 5 would be over here, 6 would be over there. Let's see, how about 15? Where's that going to live? 15 is 3 times 5, so it wouldn't be prime. It would have to, yeah, because it's not prime and it's not even, so 15 would have to live out here. Yeah, because it's not prime, it's not even. Okay, so just a note, when I do an and I'm playing around with Venn diagrams, that and is always this little crescent in the middle. That's where and lives. Or is the figure 8, yeah. So or is the figure 8, and is the little crescent in the middle. All right, so let's make it just a little bit more interesting. New page, what's that? Not quite, well, we'll keep it a little tame today. So let's switch the universe. Here the universe is gonna be counting numbers that happen to be less than 10. Okay. And then inside my universe, I'm going to break that into a couple of subsets. And let's stick again with the primes. And let's stick again with the evens. All right, so counting numbers less than 10. Well, that's 1 through 9, right? So what I'd like you to do is draw this diagram and put down where each number lives. And basically, when I put two sets in there, subsets inside, I've basically broken this up into 4 places people can live. They either live in the middle, where both circles meet, they live in the prime but not the even part but not the prime part, or they live out here in the middle of nowhere. So we have, again, 1, 2, 3, 4 places those numbers can live. Where do the numbers 1 through 9 live?
Outside.
Okay, so start labeling where they live in here. Let's see, from earlier work, I know 2 goes in the middle. 3 is prime. 4 is even. 5 is prime. 6 is even. 7 is prime. 8 is even. 9 would be outside, right? Because it's not prime and it's not even, because 9 is 3 times 3. Yeah, so 9 would be out here. Oh, I'm missing a number. There's another counting number. I missed 1. Where does 1 go?
Outside.
1 goes outside also. Yeah. Okay. So if somebody said, so I'm going to abbreviate prime with a P and E with an even, if that's okay. If somebody says, well, find me the list of all numbers that are prime and even, I would say, well, that's that intersection here, right? So 2 is the only number. I'm going to use set notation because I'm describing sets with these letters here. If I said, list me the numbers that are prime or even, well, it's everything but 1 and 9, really, but I should list them out. So that would be, what? 2, 3, 4, 5, 6, 7, and 8. And I want to pick on this set for a minute because we have to use a little bit of caution. How many prime numbers do I have in this universe? I have 1, 2, 3, 4, don't I? Okay. And I have 4 evens, right? 4 and 4 is 8. How many numbers are in my set prime or even down here? No, count them. 7. Okay. So if there's 4 prime numbers and there's 4 even numbers, how come I only have 7 numbers that are prime or even? Yeah, we don't want to double count 2. 2 is counted here, right? So sometimes when you put sets together with or, something, I don't want to list 2 twice there. If I counted it with the primes, cool, I'm done. I don't need to list it again. So we don't double list elements just because they belong in more than one set. Does that make sense? Yeah, so that's important when we're playing around, because 2 is in the intersection. So when we're counting sets and we throw an or together, or is kind of an addition, isn't it? We put them together. We put the primes together with the evens, that's our new set. But there can be a problem with double counting on an or. So one way to think about it is if you take the first set, however many are in there, add it to the second set, right? You accidentally overcount and get 8. But if you subtract that you counted the intersection twice, you're okay. Right? So counting-wise, the prime set plus the even set minus the intersection, everything works out right. All right, let's see. Sometimes, let me erase this so it's not confusing. If I wanted to look at the set that is not prime, with notation, sometimes you'll see a tilde, a little squiggle like that with the name of the set next to it. That is another way of saying not. Other places when you look up logic, they'll put a bar over the top to mean not something. Okay, so those are 3 different ways to say not prime. Just write not prime. Tilde P, not prime. P with a bar over it, that still means not prime. Okay. And in this case, if I wanted to say, well, which numbers are not prime, I could list those numbers. Well, prime is inside this circle. So not prime would be outside that circle. That would be 1, 9, 4, 6, and 8. Okay. You could shade outside that circle to demonstrate what not prime means. So anything out in that shaded region represents the not prime. And again, sometimes when we're doing logical arguments, things will pop up like, I need people that don't have blonde hair, for example. So you guys are out for now. No offense, just can't use you for today. Or maybe we don't want people with green eyes. So not comes up a lot when we're analyzing different groups. We want people with this characteristic, but not that characteristic. Okay? And sometimes to make that analysis easier, a Venn diagram can help us figure out, okay, which group do we want again? Especially if we start throwing not and or all together in the same sentence. And we've heard sentences like that before, right? So that's one thing we're going to try and do is analyze those. So let's throw something together and see what happens. How about, let's go with that same universe. Oops, that is a highlighter. I don't want that. Counting numbers less than 10. Is my universe. And I'm still going to have my primes. I'm just going to call them P, and I'm still going to have my evens. I'm going to call those E. And I want to figure out what is the set that is not, how about P or E? And so my preferred way to write that would be saying take P or E and put a bar over the top. Okay, so first thing, there's kind of like an order of operations thing going on here. Before I can do the not, I really need to understand what P or E means. Which shape is that on my screen here? The whole figure 8, right? Yeah, so or would be this set right here. So then when I move to the not means just look at everything that outside of that. So that would have to be everything outside would be the not P or E. Okay. So that means in this case it'd be 1 and 9, right, from my previous one. 1 was out here, 9 was out here. So the elements of this set, oops, that's supposed to be a curly bracket, are 1, 9 would be my answer. All right, let's look at a different set. Again, same universe, counting, let's write in black. Counting numbers less than 10 is my universe. Still going to do P, prime, E for even. This time the set I want to look at is not P and not E. So the other way I would write that is P with a bar over it, not P, and E with a bar over it. So and is described as an intersection, right? That's physically what we call it, where two things meet. So let's just double check that here. So I definitely want things that are not P, right? So I'm going to shade the not P in yellow. Not P would be everything outside of P's circle, right? Which is all that stuff is not P, true? And then I want to do not E. So let's pick, how about blue for not E? So not E would be everything outside of E's circle. What does and mean again? What's another word for and? Intersection, right? So I want to know, okay, where do these two colors intersect? Well, let's see. Do they intersect here in the middle? No. There's yellow and blue in the middle? No. Is there yellow and blue here? Is there yellow and blue here? Where does the yellow and blue happen to end up? Outside of the figure 8. Oh, wait a minute. Didn't we already do that set? Outside the figure 8, isn't that this set right here? That's kind of interesting. It's kind of messier here, but aren't we? I need to look at all the places that I see yellow and blue shading in the same spot. Where's the vertical and the horizontal shading live? Well, it doesn't live in this circle. It doesn't live in the middle. It doesn't live in that circle. It only lives outside both circles. So it looks like not P and not E is the same set as not P or E. Let's see if that makes sense. A new screen here. So P or E with the bar over it basically means I want everything that's not in P. Now, I also want to be not or. What's the opposite of or? And I want not E, so this, yeah, that's the same thing as not P and not E. That's kind of a cool little trick. There's different ways to make the same thing happen. Now, personally, drawing-wise, I thought the top way was easier to deal with than the bottom way. But a lot of people have trouble speaking that way, because notice when I wrote it down over here, I had to do not parentheses stuff in the middle. That was important. But this is a pretty important result in logic, that the opposite of an or is an and. Vice versa. What's the opposite of an and? It's going to be an or. Yeah. Yeah. Yeah, so that is a good question. So what if I had put a bar over the whole thing? Would that be different? So instead, if we looked at P and E with a whole bar over it, well, P and E would be this section right here. If I say not that whole thing, oops, oh, I made my pens disappear. That would be everything outside, like that. If I do the not. No. Does that make sense? Right? Because without the not, P and D is that little intersection. When I put the bar over, that means take everything outside of that intersection, which is the shaded blue. Let's get my magic tools back. Nope. Oh. P, thank you. There they are. Yeah, so everything outside of that intersection would be not P and E, which language-wise, again, would be not parentheses P and E. So we got to get used to the notations. The Venn diagrams can help us sort that kind of thing out. Just double check, though, according to my previous analysis, another way to write this set in symbols, there would be a not P. What would not and be? Yeah, the opposite of or, and would be or, and then not E. So let's see if we can sketch that out and see if it matches what I have shaded here. So new page, let's try that one. Let's see, black. So I want to see, what does not P or not E look like? So here's P, here's E. So let's see, I'll do the not P shading in yellow. So not P would be everything outside of P, right? And then in red, I'll do the not E. I'll do that vertically. So this is not E, not E, not E, not E. And then all of a sudden I have to start skipping E. And let's see, what does or say? Or means you have to be one color, the other color, or both colors. So basically I want anything that's shaded. Is that the same result I ended up with here? It's everything outside the crescent, right? Yeah. So there's all different ways you can put sets together with ands and ors and nots. Venn diagrams can help try and say, what set are we talking about again? They can help us clarify that. Okay. So we'll come back to Venn diagrams a little later. Let's take a look at the idea of a statement. So statement is just a simple sentence in logic. So for example, a statement could be a number is prime. Okay, so statement, one fact thing, number is prime. Now sometimes whatever that thing is could be a complicated idea. Like being prime is kind of complicated. Because if somebody says, hey, is 1,752,253 prime, I have a serious amount of work to do to figure that out because I have to see if anything divides into it. So although for small numbers, it's not too hard to tell if it's prime. For big numbers, it is. But the idea of prime is kind of simple. So that's a statement. The sun is shining. That's a statement. You can have cake. Oops, whoa, magic pen. Sorry, this thing's expensive. So just statement is just some sentence, simple sentence, fact. We're hoping to be able to determine the truth or falseness of a logical statement, but that's not always easy because it could be time dependent or place dependent. Is a number is prime? Well, you give me a number, I'll eventually figure out whether it's prime or not, and I can say true or false. The sun is shining. I'm looking out the window now and it's shining, right? Is it shining over there where you are, Fen?
Yes, it's shining.
Okay, it's shining over there. In 12 hours, will the sun be shining anywhere near any of us? No, it's not going to be shining, but it's shining somewhere. Okay, so some statements we can easily look at and figure out whether they're true or false. Other statements we can't at the moment because we don't have enough information, maybe. And then we can start putting those statements together like we were playing around with the and, the or, and the not. Okay. Other things, statements will often have a quantity attached to them. Okay. Like a number is prime. I'm talking about one number. Okay. It could be some numbers are prime. Okay. Let's see. What's the opposite of some?
All.
Because we got to negate things sometimes. What's the opposite of some? What'd you say, Fen?
All.
All? Nope.
Mm-hmm. And.
None. Yeah, none is the opposite of some. Yeah, so if I needed to negate a sentence that had some in it, I would replace the some with a none. Okay, that would be the opposite of some. And then sometimes we put statements together in multiple ways. Like we could do the and thing. Like a number is even and prime. So we can put two different statements together with an and. Another way to put two different statements together is with what's called a conditional. Another name for a conditional is if then. So let's see, two statements I had earlier. If the first statement could be the sun is shining. Then some other statement like you can have cake. Okay. Another name for this kind of statement is an implication. The sun is shining implies you can have cake. Okay. So you'll see it called a conditional. On the condition the sun is shining, you get to have cake. Implication's the same idea. Some people call it an if statement or an if then statement. Same idea. But it's another way, logically, we can put two sentences, two statements together. And these come up a lot in math and other places, like politics. Okay. If you add this thing in the bill for my county, then I will agree to the rest of your bill. Right? There's all those kinds of promises people make. If you elect me president, I will build a giant wall. If then, right? So the thing about if then statements is when are they true and when are they not true? Okay, so it depends, yeah. So let's use the sun and shining. One way to think about the truth of a statement like this is if you consider it a promise. If I break my promise, it's false. If I don't break my promise, it must be true, is the way to think about it. Okay. So the only way this can be false is a broken promise. Now here I only have two, oops, that came out very badly. Here I only have two sets, two sentences. We could have more than one in there with ands and ors and nots and stuff. So we could use a Venn diagram to play with this. I'm going to show you another tool in logic to play with this called a truth table. So let's see. My first statement I'm going to call S for sun is shining, and the second statement I'll call C for cake. So I could abbreviate that whole thing by saying I'm analyzing the compound statement that S implies C. If S, then C. And S stands for the sun is shining, C stands for you get to have cake. So those are two different ways to abbreviate that whole sentence. Because in logic, when you're analyzing a sentence, it's a pain to rewrite it over and over and over again. So usually we do little shortcuts like this. So just backing up a page. That right there is what I'm referring to as S. And this right here is what I'm referring to as C. If S, then C. And the way a truth table works, oops, wrong button. Where should I be? There we go. There we go. You just write down your first statement, S, for a column heading for a table. Your second statement, C, and then ultimately we'll get to any compound statements after that. Okay, so I only have one compound statement, S implies C. Okay, so it could be the sun is shining is true, and then I give you cake. So does that make my if the sun is shining, then you have cake, a whole true statement altogether? Yeah, the sun was shining, you got cake, the whole thing is true. Could be, though, the sun is shining, and I refuse to give you cake, so I make that part false. Did I break my promise? I did. So that means the implication is now false because I broke my promise. Okay, right? So we're trying to analyze the truth of this black sentence here, and then we look at a situation. Yep, the sun was shining. Did Gary give you cake? Nope. I lied. I broke my promise. That makes the whole thing false, right? If you're lying, something is false. All right. Now, those are the only two ways it can go if the sun was shining. But it could be the sun is not shining. Am I obligated to give you cake? No, but I'm going to give you cake anyway. There's no promise was broken, so the end result is still true. Okay? Sun's not shining. Do I have to give you cake? No, I didn't promise. I'm not going to give you cake today. It doesn't make the statement false, though. The original statement is true, still true, because I have nothing that's broken. Yeah. Did I break my promise? No, the sun wasn't shining. So basically the whole statement, I have nothing to judge it on. So by default, it's true, is the way we do it in logic. Yeah, so as long as I didn't break my promise, I'm okay. So that would be the truth table for S implies C. So that's the way I often read that. S implies C. That's how you could read that. And it could be a really complex statement with, you know, an S, a C, and another statement called D, and throw an and in there. When you do a more complicated one, you just keep doing one column at a time, and eventually you get to the end. So let's try a more complicated one. But I always, just when I took logic, and even years later, this last one always threw me. That one gets to be true. But the way to think about it is, if a promise wasn't broken, it's not false. It gets to be true. Okay. Yeah. So because if it's broken, that means it's false. So that means we must be not false. Well, what's not false? True is the only thing that's not false. Yeah. So I'm stuck with that result, that verdict. Okay. All right. Let's say, what things can I put together? Let's stick with S. The sun is shining. C, you have cake. And how about H, you are hot, as in warm, not attractive. I'd have to explain that to usually my 15-year-old daughter. She uses the word hot all the time. Okay, so how can we put these together? Let's suppose we want to analyze the statement. The sun is shining, and you can have cake if you're if you're hot. Oh, that's a good one. Okay, so let's see. Oh no, that's a better idea. Okay, let's erase this. That was good. I wasn't thinking that. That's even more interesting. Control Z. Okay, oops, I need to undo more of that. So how about if the sun is shining and you are hot, then you can have cake. Okay. So another way to write that whole compound statement would be to say, with even more symbols, actually, let's make it even more exciting. S an upside down U sometimes. Sometimes it's an upside down like arrowy thing. Depends on what book you look in. There's a couple of ways to write it. Oh, my tools are missing. Control T. Oh, there you are. Yeah. Let's get rid of that. So I'm going to use that symbol there. H. That goes in parentheses, and then an arrow over to C would be another way to write that. So depending on what book you look at, where you look online, you'll see slightly different notation for things like this. So to analyze this statement with a truth table, since I have three things happening in pieces, I'd have to analyze them in pieces. So let's set up a truth table for that whole combination. S and C implies, no, S and H, sorry, implies C. So in my table, first thing I'd want to do is figure out what are the possibilities for S and H and C all by themselves. Order of operations for this statement, the parentheses indicate them. So the next thing I would have to analyze is what are S and H doing. And then finally I could put them all together and have S and H implies C. So for any connection, it needs its own column. So there's a connection for an and, it needs its own column. There's a connection for the implication, it needs its own column. And then each of the individual pieces need their own column. Okay. So then when I go through and I just start with the S, I usually say, okay, what if this is true? Well, this could be true too. It could be, you could be hot, and you could get cake. Okay. Next thing I might do is say, all right, this could be true here. We could keep the hot true, but you don't get cake. Okay. I left these the same and I changed those two. Would you agree I'm done leaving those the same? I ran out of options. So then I'm going to have to go, okay, keep this true. Let's make this guy false and this guy true. Leave the first two the same still. True, false, switch that one to false. You're going to see a pattern here as I go through this. Evolve. Okay, I'm done with my true, false here. So what do I have to do next for the S's? Yeah, I got to go down to false next. And I can let this one be true and that one be true. Hold on to that false. I can still hold on to that true here if I let this one be false. So what I'm trying to do is how many different ways can I put these things together? You see a pattern evolving here? True, 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 false, false. True, true, false, false. True, true. Oh, what do you think is going to be next? Maybe, how about this side? True, false, true, false, true, false, true, false. Let's just double check that that happens. I kept these two the same and I switched those. I got to switch this one next. So this is going to be false, false, and then usually I like to start with true. I can let this one stay false and that one false, and then that one has to be false. So the pattern goes, this one alternates strictly, this one alternates in pairs, and then we double, this one alternates in fours. If there was a fourth thing, what do you think it would alternate as? Eights, yeah, because this goes 1, 2, 4, we double each time. We would have 8 by 8. Yeah, so it's powers of 2 that we end up seeing here. Yeah. All right. And I'm only focusing on the S and H, so C stays silent. It has nothing to do with it. For and to be true, what has to be true about the two things I'm playing with? They both have to be true, yeah, so that's it. So let's switch color. So as long as S and H are true, the and gets to be true. As long as S and H are true, the and gets to be true. But as soon as one of them decides to not be true, the whole thing is stuck being false. So and means both conditions have to be true to stay true. Yeah. So it's going to be anytime one of them is false, we're false. So we're true here. Otherwise, we're false. We're false. We're false. We're false for the rest of the tree, or the table. False. False. So in this case, the and is mostly false. Okay. Now the implication is only if the promise is broken, right? So that's my next column, right? The implication here. So if we look back at our implication's pretty straightforward. This is the only time the promise is broken. Otherwise, the implication gets to be true. So let's see if we can figure that out for this more complicated table. Let's see. So all I have to do is look at the blue stuff now to start with. That's true. C is true. So the whole thing gets to be true. The and is true. Sun is shining and you're hot. Did we break a promise? Yeah, so now it's false. Sun is shining and hot, that's false. Does it matter whether we give them cake or not? No, because the beginning part was false, doesn't matter, it gets to stay true. Promise was not broken. Well, here, the sun was not shining and you weren't hot. You didn't get cake, so what? You didn't meet those both conditions, so I am not obligated, right? So it's still true. Promise is not broken. False, true. It's still true. False, false. No broken promise, still true. False, true. Still true. False, false. Still true. Yeah, the implication's not that bad. It's mostly going to be true. The and is the fussy one, right here. Yeah, so that's the truth table here. So given some kind of complex sentence, a truth table can tell you whether the whole sentence is true or not based on the pieces of the sentence being true or not. So that's the point of a truth table. Is it easy? No, but if you think I just do one part at a time, it's not too bad. There's no way you can do the whole table at once. So like if you look at the online book, there's some complicated ones in the middle of the book. Let's take a peek. Here we go. So later on here, there's some crazy truth tables. Where are they? Oh, here we go. That's an easy one. That's not bad. That one's a little, that's about what we just did, similar. I guess they're not much worse. Ooh, those are going to be fun. But we're about out of time. I don't want to burn you guys out. All right, so there's one, we'll do more with these truth tables and implications next class. Again, there's some more terminology. So again, if you haven't started reading the stuff, try to read it. You should play along. Anytime they give an example, you should try and make sure the example makes sense to you, penciling and stuff if you can. One more quick idea, and then we will get out a few minutes early. Computer on a spreadsheet. You can have conditional statements in a spreadsheet, and in a spreadsheet, it's called if with a parentheses after it. And remember, you always put equals in front if we're on a spreadsheet. So I'll describe what it does, and then I'll demo it. So on a spreadsheet, the way the if works is the thing that comes first is your condition. Like, is something prime? Right? We'd have to teach the spreadsheet how to check that. Is a number less than 10? Right? It's something a spreadsheet can check. Then there's a comma. And then what to do if the condition is true. And then there's another comma. And then what to do if the condition is false. Okay. So a simple statement kind of on paper for that would be if some cell on the spreadsheet is less than, say, 10,000. So if that's true, then give us an answer of 0. If it's false, then take 10% of whatever was in that cell. So that's an example. Like, think about taxes. If you don't make enough money, you don't have to pay taxes. Or tax brackets. If you make over 20,000, we're going to put even more taxes on you. Right? You're going to pay, instead of 10%, you're going to pay 20%, for example. Right? Yeah. So that's the kind of thing accountants do with an if statement. Right? So let me just set up a spreadsheet that uses that so you can see how it works. So I like to use Google Sheets. So I'm going to jump in there. And let's start with a blank sheet and blow it up a little. Okay, so suppose here is income. Blow it up a little more. And the income could be, 5,000 or 8,000, 10,000, 12,000. Oops, too many. 5,000. So on. Nice thing about a spreadsheet, I don't type the $sign, I just highlight them and then click the $sign button and it makes them nice for me. Okay. And then here's my condition. I want to check to see if the income is less than $10,000. And so I'm going to use that statement I just went over. So there's two ways to make that happen. If you already know how to type it, you just start typing whatever you need to type. If you're not sure how to type it, there's an insert function wizard here somewhere, right here. I click that button. Do I see an if in this list? Nope. So then I jump over to more functions, and then it'll tell me, I can search if. If comes up a lot here. Are they in alphabetical order? Oops, did I miss it? A, B, C, D, O. Where the heck is it? Huh. How about condition? Weird. Why doesn't it just say if? Huh. Okay, usually they're easy to find. I don't know why it's not giving it to me there. Anyway, so if I start over here, I type equals if, it'll list things and tell me what they are. So returns a value depending on a logical expression. So I click there. And if I hit the question mark and click back on it, it says, okay, what's your logical expression? So my logical expression looking back here was if some cell is less than 10,000. Well, which cell? How about the cell right next to me? So I just click on that cell and I say, okay, are you less than 10, 1, 2, 3? Okay, comma. What to do if it's true? What did I say I was going to do if it's true, if it's less than 1,000? Yeah, there's no taxes, right? So I'm going to go 0. Comma, what to do if it's false? So then I'm going to take 10% of it. So 10% means I'm going to have to go 0.1 would be 10% times whatever's in that box. Okay. Then I close the parentheses and hit enter. So is that number less than 10,000? Yeah, so that means when I hit enter, I should get the value 0. There's my 0. Now, do you remember there's a trick about formulas? If I want to use the same style formula below, what do? Yeah, I just drag it down. So first I click on it, let go of the mouse, point to the bottom right corner, click and drag. And what that'll do is it'll change the A2s up here to A3s, then A4s, then A5s, and so on. Okay. So if I double click here, notice it switched the A2s to A3s. Is this less than 10,000? Yeah, so I got a 0. Okay. 10,000, is that less than 10,000? No, it's equal to, so that means we jump to the next position, which says take 10% of me, which is 1,000. So it worked. I applied the condition. And it turns out you can do more complicated conditions like I need the number to be greater than 10,000, greater than or equal to 10,000, but less than 20,000, right? So I can do tax brackets. with something like that. So I'll show you how to set up a tax bracket next time. So your job is to start reading through the textbook stuff, start playing with the online homework. You'll be able to do some of it now. Did I ever give you the logic thing? Oh, it's sitting on the printer. Just go grab one off the printer. There's 3 of them out there, whoever needed one. All right, so that's it for today.